help.
Okay.
Thank you.
So good morning, and I'm Valentina Cacchiani from the University of Bologna. And today I want to present some algorithms for train timetabling problems, and in particular algorithms which are based on modeling the problem on a time-expanded graph. So this is the outline of my presentation. First, I will introduce the train timetabling problem, and then I will present two mathematical models based on time-expanded graphs, and then some solution methods for these models. And then in the second part of my presentation, I will show how to generalize these methods to handle some additional real-life features that appear in some case studies that we did in our application. So let's start with the introduction. And here you see all the railway optimization stages. Because railway optimization is a complex problem, it's always divided into different stages. And each of these sub-problems is actually an NP-hard problem. The first one is network design. And this is basically to define what is the infrastructure we have to consider. So how to construct stations and then tracks connecting these stations and the number of platforms in each station. So design the infrastructure. And the second stage is the line planning problem. In this case, we want to define the lines in our network, where a line is basically defined by an origin station and destination station, and then a set of stops along this route. These two problems are solved at a strategic level because the decisions of these two problems basically lasts for several years. And then at tactical level, we have, first of all, the timetabling problem. So the timetabling problem is the problem in which we want to determine which are the best timetables for a set of trains. So we want to find the schedule for the trains given by departure and arrival times of all trains in our network. After we have found the timetable, then we have the rolling stock planning problem, in which we have to assign the physical trains, so locomotive and cars, to a set of trips in order to perform the timetable that was previously decided. And as a last step, we have the crew rostering problem, in which we have to define the roster, so the duties for all crew members. And of course, this must match both the timetable and the rolling stock planning. After the tactical level, we also have the recovery that can happen in real time, because of course there can be some delays or disruptions that can happen, and then we have to make the timetable, rolling stock, and crew rescheduling because of these disruptions. So in this presentation, I will focus on the train timetabling problem. And as I said, this is to derive an optimal schedule for a set of trains in a network. And we have to satisfy some constraints, for example, safety regulations that require a minimum headway time between consecutive trains on the same track. This is just for safety. And then some operational constraints. For example, we have a maximal speed for each train, so we have some limits on the running times. Then we have some constraints on the dwell times because we have to let passengers get on and off the train. We have a station capacity, so the maximum number of trains that can be simultaneously present at a station. And what we want to find is the schedule defined by departure and arrival times of trains at all visited stations. So basically, the output is what you see here on the right. For each train, the list of stations it visits and the corresponding time. And then the objective function depends very much on the railway company. So there are many different objective functions. As an example, we want to schedule as many trains as possible to provide a good service to the passengers. So the train timetabling problem comes after the network design. So the railway infrastructure has been already defined. And the railway infrastructure is defined as a set of nodes and a set of tracks. Nodes represent locations where the trains may interact, for example, stations. And the tracks then connect the nodes and represent the travel of a train from one node to another. And here you see two infrastructure in China and in the Netherlands, because these are the two applications that I'm going to present later. And another input that is given to the train timetabling problem is the list of trains to be scheduled. This comes from the line planning, the other problem that is solved before train timetabling. And this can be given into two different ways. The first case is when we give a set of train lines and then for each line we specify the frequency. So for example, we specify that our line from Milan to Rome, we want a frequency of 2 trains per hour. And then we have to find the schedule for these trains. The second possibility is that we give the ideal timetable for each train. So basically, we already get in input to the timetabling problem the list of all arrival and departure times for every train. So already a timetable is given by a train operator, and this is computed again based on the passenger demand. But altogether, these timetables are not feasible. So we have some conflicts, and then the problem of timetabling is to find a feasible schedule, so a conflict-free schedule for our set of trains. As a constraint, we have, as I said, some constraints for safety, so minimum headway between consecutive arrival and departure of trains on the same track. We must forbid overtaking and crossing of trains if they travel on the same track and there is no siding. And then we have some lower and upper limits both on the dwelling time and on the running time of each train. And then we have to account for acceleration and deceleration times when a train stops at a station. In addition, we can have this maximum number of trains that are simultaneously present at a station because of the number of existing platforms. And we can also have some connection constraints between trains if passengers have to transfer. So we want to account for this additional restriction. And many others, okay, depending on the railway company, we can have different sets of constraints. And in particular, we distinguish between two types of timetabling. One is called periodic, and in this case, the schedule of the trains is repeated in the same way every given time period. For example, every hour. So for example, we have a train from Bologna to Florence at 9:15, and then it's again at 10:15, at 11:15, and so on. So this is very good for the passengers because then they can remember easily the schedule, but not always possible to do it depending on the type of the network. An alternative is the non-periodic schedule. In this case, actually, there is a sort of periodicity because the schedule of the trains is repeated in the same way every day, but it's called non-periodic because, of course, the passengers cannot remember the schedule in this case. And this is more appropriate when we have a more congested network, especially if we have different kinds of trains on the same infrastructure. For example, freight trains, local trains, high-speed trains that share the same infrastructure, then it can become difficult to have a fully periodic schedule. In this presentation, I will focus on starting from ideal timetables given for each train. So we already have a set of timetables, which are the desired ones. And as a focus, as a goal, we want to schedule as many trains as possible, but also minimize the changes with respect to these ideal timetables. Some changes are necessary because we have to make a feasible timetable. And then I will first focus on the non-periodic problem, and then later to the periodic one, if I have enough time. So let's see some mathematical models, as I said, based on time-expanded graphs. And as I said, we focused on non-periodic timetabling. And here I'm showing the model for a one-way line because it's simpler, but actually it has been extended already to deal with the network. So in this line, we have a set S of stations from station 1 to station S, and we have a set T of trains. And for each train, we know the importance of the train, so sort of priority. For example, if it is a high-speed train, has a higher priority than a local and higher priority than a freight train. And we also have this ideal timetable. So we know for the train the departure and arrival time at each of the visited stations. And then we consider a time discretization to have this time expanded graph. For example, 1 day divided into minutes. And our goal is to maximize the total number or total importance, considering these priorities of the scheduled trains, and at the same time minimize the changes to the ideal timetables. Which changes do we apply? So first of all, why do we apply changes? As I said, we apply changes because maybe these timetables usually are infeasible altogether. There are conflicts. So we need to apply some changes to make the timetable feasible. And this is the list of changes that can be applied. So we can change the departure and arrival times of trains at some of the visited stations, which is called a shift. And we can also increase the dwell time of the trains at some visited stations, and this is called a stretch. And we can also cancel a train, which actually in this case corresponds to not scheduling the train at all, because remember that we are solving this problem in planning. So this is to find a timetable that will be then published to the passengers. So we decided that maybe it's not possible to schedule this specific train. And we also have sometimes lower and upper limits on these changes, because we maybe, if we have, based on passenger demand, we want to schedule a train at 9, and then we make a shift, it is scheduled at 10, maybe this is not very useful for passenger demand. So there are limits in the changes that we can apply. And for the total stretch as well, because of course, if we have an increase in the dwell time, then also the total travel time for the passengers increases as well. So what is this time expanded graph? So this model, time-space graph model for this train timetabling problem was proposed by Caprara, Fischetti, and Toth in 2002. And we consider this graph G. And this is an example of the graph. So here you see 1, 2, and 3 are 3 stations. And then for each station you have a line, and this line is the time. And each of these nodes corresponds to a departure or an arrival time of a train at a station. And we have to decide which ones should be the good ones. And you can also see some arcs which are selected here. A segment arc which represents the travel of a train from a station to the next one, and the station arc which represents the stop of a train at a station. So basically we have set V, the set of nodes, which is given by all train departure and arrival times from every station in the network. And then we have a set of arcs, travel and station arcs. In addition, we also have the starting arc and ending arcs, because we add just for convenience a source and a sink node. And these arcs are partitioned for different trains because different trains can have different travel times and can also have different dwelling times. And now the problem is to decide which arcs we need to select. So we can have a variable, binary variable, that is 1 if arc A is selected. And we need to select arcs so that we compose a path in this time-space graph, because a path corresponds to a timetable for a train. Here it's a path that is both in space, going from station 1 to station 3, but also in time. Depending on which path we select, we have a different timetable for the train. So here is an example in which you can see 3 timetables for 3 trains. These are given in input. We have 5 stations. And then we have, for example, for the first train, departure time in the ideal case should be at 9 from station 1, arriving in station 2 at 9:05, then stopping there for 2 minutes, and then arriving station 3 at 9:18. And all these timetables can be represented by these paths in the graph. So the first one is on the left here, this dotted path corresponds to the first timetable. And then you can see here some parts of this figure which are highlighted in bold, which represent the conflicts between trains. For example, there are two trains, the first and the second one, which are departing exactly at the same time on the same track. We are considering just a single line, so it's not possible. And also there's a conflict between stations 3 and 4, where there is an overtaking between two trains, but actually there is no siding. So this would correspond to an accident between the two trains. So to get a feasible set of timetables, then what we can do is to change these timetables by shifting, stretching what is given on input. So this is a possible solution where, for example, the first train is shifted in advance of 2 minutes. And then we have a stretch here for the train in station 3. It stops more from 9:30 to 9:41. And in this way, we don't have any conflict. So our mathematical formulation is then the following. So we have maximization of the total profits for all selected arcs of all trains, where the profit is used as a number associated with each arc, representing the importance, so the priority of the train, minus the penalties for the changes that we apply. So if we don't apply any change, we get the full profit. If we shift by 1 minute, the profit is decreased. If we stretch, again, the profit is decreased by some penalties. And then we have some constraints, because for each train, we must identify at most one path in this graph. At most one, because we allow for canceling trains. So starting from the origin node, this source node, we must select at most one arc, and then we have this flow conservation to define a path, so a timetable in our graph. And then we have additional constraints, which are actually the hard constraints, because we cannot have conflicts, and this means that among a set of pairwise incompatible arcs, we can select at most one. This is for the first kind of model, and then we can have a second model based on path variables, which basically is very similar, but now we have a variable for each path. The variable is 1 if this path is selected, and we maximize the total profits for all selected paths. And in this case, we are directly selecting the full path for a train. For each train, we cannot choose more than one path again. And we have some limits on the set of paths that we can select because we cannot select conflicting paths. Now, these are two relevant models based on time-expanded graphs. And now we can see how to solve these kind of models. So some solution methods. The first solution method that I want to show is a Lagrangian-based heuristic algorithm. That is the one that I actually will use in the following two case studies. So this was proposed by Caprara, Fischetti, and Tot in the same work, and then we extended it to deal with the network. So the model is the algorithm is applied to the ILP arc model, so the first one that I presented. And what we do is relaxing all the incompatibility constraints in a Lagrangian way. So basically, because we have these hard constraints of conflicts between trains, we relax them in a Lagrangian way. And in this case, we can identify, we can compute an upper bound for our solution. And then we apply subgradient optimization to determine near optimal Lagrangian multipliers so that we can get a better upper bound. And also we apply dynamic constraint generation because the number of constraints is large and we want to avoid handling all the constraints simultaneously in the process. In this way, we get an upper bound, and then to get a feasible solution during this subgradient optimization, each iteration, we also compute a heuristic solution, by first ranking the trains according to the Lagrangian profit, which means considering the original profit of all arcs in our network, and then also taking into account the penalties for the violation of these incompatibility constraints that were relaxed. And then once that we have ordered these trains, we schedule them one by one. Every time we schedule a train, this path is fixed and the other train cannot select anything that is conflicting with this previously selected timetable. And this is obtained by dynamic programming algorithm, because basically we have to compute a path in this graph. And finally, we also have some local search procedures just to improve the solution found. A second method is instead an exact method, is a branch and cut and price algorithm, which was proposed in this work, and is applied to the ILP path model, so the second model. In this case, we first solve the continuous relaxation of this model by column generation. And also we use dynamic programming here to derive the optimal paths in this time expanded graph. And also here we apply constraint separation for the same reason. So we have also here a large number of constraints. And then we apply branching to find an optimal solution. And the branching is on the choice of the arcs in the graph. And this is an exact algorithm, so usually it requires quite a long computing time. So if we have a very large instance, then it becomes difficult to obtain an optimal solution. And for this reason, also based on this ILP path model, we can use some constructive heuristics. For example, variable fixing based on the continuous relaxation solution, which can be fixing paths or fixing arcs in our graph. So these are two models, two algorithms for our problem. And then I want to extend them to include some additional real-life features. And the first one is a skip-stop planning strategy. So skip-stop planning strategy means that we have basically in our set of options for the changes that we can apply to the timetable, we also have the possibility of skipping a stop. Skipping a stop, again, because we are in planning, it means that we decide not to schedule a stop. So this is an additional possibility to get a feasible timetable. If there is a conflict, maybe we can skip a stop and then there is no issue between these trains. We applied this to the high-speed double-track line between Beijing and Shanghai in China. And the goal for this problem was to increase the capacity utilization of this line. They have many passengers traveling along this high-speed line. They already had, at that time, about 300 trains scheduled every day. But then they wanted to increase this number. And so the idea was to try to schedule additional trains and considering also this option of skipping stops for some trains, if it is possible to schedule more trains. So we started with given two sets of trains. The existing trains, these 300 trains for which we already have an actual feasible schedule, and then a set of additional trains that we want to try to schedule. And for these trains, we know these ideal timetables, which are provided again by the train operator in order to have a good match with the passenger demand. And then we had some constraints in addition to what I listed before, this minimum headway, running time, dwell times, and so on. We also have to account for acceleration and deceleration times, especially because if we skip a stop, then we can have different options. And the acceleration and deceleration times for these high-speed trains is quite relevant. So we cannot avoid assuming that this is just a zero. And also we have constraints on the maximum number of stops that can be cancelled for each train, because we don't want to have a train that doesn't have any stop, basically. And also we cannot apply the shift operation, so this change in the departure time from the origin for the existing trains. To solve this problem, we decided to use this ILP arc model, so with the arc variables that are selected in our graph, with additional constraints because we have some more constraints in this application. And then we applied our Lagrangian-based heuristic algorithm, which is extended to deal with the skip-stop strategies. And these are handled directly inside the dynamic programming algorithm. And here is basically what happens in the dynamic programming algorithm. So each figure shows two stations, station 1 and station 2. And then there is a travel of a train from node V to node U. And there are 4 figures because the train can avoid the stop in S1 and in S2. So we have just the minimum travel time, or in the last figure, it stops both in S1 and in S2. So we have a minimum travel time plus acceleration and deceleration. And then the other 2 cases where it stops only in S1 or only in S2. So basically inside the dynamic programming algorithm, we have an additional state to decide if we stop or not at each station. And then for each decision, stop or not, we have this vector of elements which correspond to the consumption of our resource, that is the maximum total stretch along the entire path. So remember that we can apply this stretch operation that is basically increasing the stopping time along the path of the train. And if we increase the time in one station, then we are consuming some resource, some stretch among the total available one. So we need to consider stopping or not stopping, and then for every possibility of values for this maximum stretch. So we applied this algorithm to solve this instance where we have 304 existing trains and we want to schedule 42 additional trains. And this is the red line here from Beijing to Shanghai. And we have some constraints in this application. In particular, we allow to cancel at most 1 stop for each train. We have the maximum stretch, which depends on the travel distance from the origin to the destination of this train. And then we have different options for the maximum shift at departure that are plus or minus 10 minutes or 20 or 30 to allow more flexibility. And here are some results of our experiments. First, I'm showing the results when stop skipping is not allowed, which means that we can shift and stretch trains. We can avoid to schedule a train, but all stops are fixed. So each row corresponds to an option for the shift, so 10, 20, or 30 minutes. And we would like to schedule a total of 346 trains, so the 304 plus the 42. And then we have this column on the number of scheduled trains, that is our solution. So how many trains we are able actually to schedule. And in brackets is a number if we have to cancel some existing trains. So in the last row, we are able to schedule 336 trains, but 1 is actually cancelled for the existing trains. And then you can see that the profit is increasing and the gap is the optimality gap, so from the upper bound, and we have a gap around 3 or 4%. The computing time is about 3 hours and a little more, but actually this is a planning problem, so this is still an acceptable computing time. And then we consider now stop skipping. So same situation, same kind of table, but now we allow for skipping stops. And we can see that we reach this larger number of scheduled trains, 337, when we have possibility of skipping stops and a shift up to 30 minutes. And the gap is again around 3 to 4%. And the number of stops that are skipped is very low. So just 2 or 3 stops are skipped in total among all trains. The computing time increases because now we have in this dynamic programming algorithm to consider all these possibilities for stopping or not and acceleration and deceleration times. But still, I think it's acceptable because then the timetable will last for the several 6 months or up to 1 year. So this is still something that we can afford, let's say. And now I move to the second application in which instead we are focusing on passenger-centric objectives, which means that what we want to do is to derive a timetable that is the best possible timetable for passengers, so from the passenger perspective and not only the operator perspective. In this case, we have a periodic problem. And we get from the line planning problem for each train line the frequency of trains. So again, we get, for example, that from Milan to Rome, we want to have 2 trains per hour in this period. And usually in the literature, once that you have this frequency, what you do is imposing some regularity constraints between trains of the same line to provide a regular service to the passengers. So, for example, you impose that one train, the time distance between 2 trains must be 30 minutes because you have 2 trains per hour. However, this is good for passengers if they travel from the origin to the destination of the train, so they go along this line. But often passengers have to transfer between different lines. And then in this case, it becomes very important to have synchronization between different train lines. And so instead of imposing these regularity constraints that maybe can be difficult to understand what is a correct set of constraints to also have good transfers for passengers, we decided to synchronize trains and achieve regularity by minimizing the total perceived passenger travel time. So what is this total perceived passenger travel time? It's given by the in-train time, so the time spent on the train, transfer time to transfer from one train to another, a transfer penalty because usually it's not very nice, let's say, to transfer between different trains and there can be problems in the connection. And an adaptation time. Adaptation time is used to model the fact that when I want to depart at a certain time, maybe the train is not available at that time and I need to adapt to depart at a different time. So my desired departure time is at 9:30, but then the train is scheduled at 10. So I need to adapt by 30 minutes. So it's a waiting time at origin station, which is not a real waiting time, so I will go to the station when the train is available, but I need to adapt my itinerary based on when the train is available. So the idea is then to minimize this total passenger perceived travel time and find the best possible timetable. So we consider this for a period of 1 hour because it's periodic. It's a case study of the Netherlands Railways in which they have a fully periodic timetable. And we start by given passenger origin destination pairs, basically the train lines defined in the line planning problem. And then we pre-compute a set of routes for each OD pair that is given by the direct travel option to go from this origin to this destination, if possible, and then a set of routes with up to a maximum number of transfer options. And then we also know the number of passengers for each OD pair, like the estimated passenger demand. And what we need to do is to define the time of departure and arrival events. So basically, we have to define the timetable of our trains identified by these pi variables. And I'm not showing the model because it's very complex. I'm just showing it at a high level. So what we want to do is to find a feasible timetable, which means respecting all infrastructure constraints. So again, safety regulation, operational constraints on the minimum running and dwell times. And we want to find a timetable such that it minimizes this average perceived travel time for each OD per K. So this Rk of pi depends, of course, on the timetable that we select, and we have one for each OD pair k, and then we sum over all OD pairs and multiply by the number of passengers of this OD pair to account how many passengers will get this specific train, so how they affected by our timetable. And in the choice of the timetable, in the decision that we have to make, we also have to account that passengers will take best route by direct option or by transferring between trains with respect to the timetable that we determine. So we want to simultaneously decide the timetable and considering the passenger choices so that in the end the average perceived travel time is the minimum possible one. So this is, I skip this, it's just the definition of the perceived travel time in detail. So just remember that this is given by the adoption time, W, plus the in-train time and transfer time, including the transfer penalties. And then we have to account for how many passengers basically will get this specific train route. And this depends on the choice of timetable that we do and how many trains do we have in this specific hour. So this problem can be modeled as a periodic event scheduling problem with some additional constraints. And this periodic event scheduling problem is a problem in which we have these variables pi to define the time of all events in the network, and the events are departure and arrivals of trains from stations. So we define the timetable by defining these variables. And then we need additional constraints to compute the passenger routes and as a consequence, the average perceived travel time. If we model this problem as a PESP, then we can solve it with the CPLEX or with a MIP-based heuristic to improve a little bit the computing time. But actually, the solving the model has a very long computing time for real-life instances. I will show the computation time. So this is very long, and we decided then to have another approach, which is basically using a PESP, but without infrastructure constraints, which means that we allow conflicts between trains. So basically, we derive a set of timetables which are good for passengers, but cannot be executed because of conflicts between trains. And then this is combined with an algorithm based on a time-expanded formulation. So more in detail, what we do is removing from the PESP model all constraints on timetable feasibility. So we allow conflicts between trains. And then we compute in this way, by solving this simplified PESP, the passenger ideal timetables. And then we make these timetables feasible. So we remove all conflicts between trains by modifying the ideal timetables as little as possible, and we do that by our Lagrangian heuristic. So basically, again, this Lagrangian approach based on the ILP arc model. And once that we have computed this timetable, we evaluate how good or bad is the quality of the timetable for the passengers. So we again compute what is the passenger perceived travel time. And if this is not good for some OD pairs, then we apply a feedback mechanism. So this feedback basically identifies which are the OD pairs that have a bad perceived travel time. And then among all of them, we take the ones that got the largest worsening, so for which the passenger travel time is very bad. And then we modify in the Lagrangian algorithm the profit for the arcs to be selected so that we penalize more the shift at origin and intermediate stations where the service was not regular, so where the passengers had to wait too much or where they had a long waiting time in some stations. We modify these profit structures, the profit for the arcs, and then we apply again the Lagrangian algorithm. So now I just want to show our case study. So we consider 3 networks in 3 instances in the Dutch railway network. Again, the time period is 1 hour. And the first on the left is called A2. It contains 34 stations, 20 trains, and 891 odd pairs. And then we have Rotterdam, Groningen, and extended A2, which are 2 networks with the increasing complexity in the number of stations, trains, and odd pairs. And here is the process, how it works for the first instance. So this instance on the left, this A2. On the left, you see the ideal timetable. So basically, you have a time-space diagram. So you have the stations on the vertical axis and the time, 1 hour, on the horizontal axis. And all these lines are the timetables for the train. So these paths in our time-space network. And the circles above and below show that there are conflicts between trains. In particular, on top, we have a conflict because there is a single track line, and we have 2 trains that are crossing the line at the same time. So this is, again, an accident between 2 trains. And below, we have 2 trains which depart exactly at the same time from the same station on the same track. So this is also not possible. And on the right, you see a modified timetable, that is the feasible timetable computed by the Lagrangian heuristic. So some trains have been changed. You see that there are different stopping times, and now the timetable is feasible. So now that we have this feasible timetable, what we want to do is to check how much it affected the passengers. So we compute what is the increase of the passenger travel time with respect to the ideal one. So here you see these points. So when you see 0, it means that we are fine. Basically, it's the same as in the ideal case. And if you go above, then it means that some odd pairs, in particular here from Utrecht, got an increase, a very large increase for the passenger perceived travel time. And now we apply our feedback mechanism. So we change the profit structure for these odd pairs, and we repeat the Lagrangian heuristic. And now we get a new timetable, which corresponds to these blue points. And in particular, you see that the 2 red points now are down on line 0. So we get an improvement for all passengers. As a last step, I just want to show a comparison for our 3 instances with the solution of the full PESP model. So first, here I'm showing what happens if we apply the PESP to get the ideal timetables plus the Lagrangian heuristic. And 100 is just a number to identify what is ideal, and then we have an increase. So we get a larger passenger travel time of 0.18%, with the 2 hours of computing time as a time limit for PESP, and then the remaining time for the Lagrangian algorithm. If we also apply feedback, then you see that we have an improvement. So now the increase is just 0.1%, and the computing time doesn't increase too much. If we consider the full PESP model, so the PESP with the passenger, timetables, but also all infrastructure constraints to avoid conflicts between trains, after the same computing time, we get something that is worse. And even after 8 hours of computation, we don't get anything better. As a comparison, the lower bound computed by Cplex in this solution of PESP is 97, so we don't have a very large optimality gap. For the other instances, here you see Rotterdam and Groningen, which is actually basically the same situation. So now we have 4 hours of computing time in our case, and we got an increase in the passenger perceived travel time of 0.55%, so not very large. And by allowing more time for PESP, we still don't get anything better. And for the largest instance, it's even more evident because the full PESP, even after 16 hours of computing time, is not able to find any feasible solution. So in conclusion, I can say, I would say that time-expanded formulations can be effectively used in heuristic algorithm to deal with some real-life case studies. And we are able to compute efficient timetables in planning, which is very good. But actually, we also know that delays and disruptions can always happen in real time. Often we have to face them. And what can we do in this case? And this is actually the topic of the talk of my colleague Andrea Dariano, who will talk about efficient methods for train rescheduling during rail operations. So even if the timetable is good in planning, maybe in operations there can be some issues and they can be actually handled by some efficient methods in real time. And this completes my presentation. Thank you very much for your attention.
Thank you, Valentina, for the presentation. So once again, if people have questions, you can raise your hand or you can ask them in the chat. We did not have a lot of raised hands for the moment, so don't hesitate.
It's the lunch time.
I have a question. You have two objectives. You want to maximize the profit, the number of trains, and to minimize the number of changes. Very interesting in these two objectives because I worked on a robust approach which considers them too. I was wondering if you could explain again how you handle both of the objectives.
Yes, so basically it's hidden inside the definition of the profit for each arc. Okay. So when we have the starting arc for a train in our network, we can assign to this arc the profit given by the value of the train or the importance. So suppose I say the high-speed train has profit 1,000 and maybe the freight train has profit 500. So I give different priorities to them. And then if I change the departure time with respect to the original, the ideal one, by 1 minute, 1,000 becomes 999. And if I move again, it becomes 998 and so on. So for each arc, I can pre-compute exactly what is the profit for this arc. And when I select my arcs, I'm already accounting both for the importance of the train and for the changes, for the penalties.
And how did you choose the weight between the profit and the changes?
Yes, so this is a very hard problem, basically. So let's say that they are some way defined together with the operator. So, for example, in our experiments, what we did was giving a large value to the profit of each train because we want to schedule as many trains as possible. So it's better to move the train from the ideal timetable even a lot, but scheduling the train anyway. And then shifting and stretching, these two operations are usually assigned different penalties. The shift is usually lower with respect to the stretch penalty because the shift means that the departure will be in a different time with respect to the ideal one. But the stretch means that the passenger will be on the train for more time because the stretch is stopping more at the station. So, and skipping a stop is given an even larger penalty because usually if there is a stop, it means that there is a passenger demand. So avoiding a stop is not good for the operator because it means they get less money from selling tickets, basically. So these weights are decided together with the operator. And then actually what we did, for example, in this last case on passenger-centric objectives was to test many different profit structures. So penalizing more shift and less stretch or vice versa, or giving different values for different trains. So it's something that clearly affects a lot the solution to the problem. So it's it's a choice that we do, but it's like in weighted sum problem. So it depends on the choice. So.
Okay, thank you, Valentina. I don't see any more questions, so I think we will stop there. Thank you to all the speakers of this morning.